Now we go on to another speaker who also has been on planetary radio, and we are very honored to have him here. He is the project manager for the Hayabusa mission, mission of JAXA, the Japanese Space Agency, that has been very, very successful at encountering and orbiting asteroid Itokawa and sampling, and hopefully they've had some issues, but hopefully we'll still be able to get their spacecraft back for the first sample return from an asteroid. Again, we are very honored to have him here, Junichiro Kawaguchi.
Good morning, everyone. I'm Junichiro Kawaguchi from the Institute of Space and Astronautical Science, ISDC, or the Japan Aerospace Exploration Agency, JAXA. I'm going to talking about the Hayabusa mission. There is the world's first sample return mission from an asteroid. The significance of having the sample return wasn't stressed by the previous speaker already, so I do not repeat it. What the Hayabusa mission is briefly summarized here in this slide. It's the world's first interplanetary stopover round-trip flight, making the challenge of collecting the sample of the asteroid. It's a technology demonstration mission, still having the scientific objectives. It was launched in 3 years before, May of 2003, and it wasn't propelled by the ion engines, and also combined with the Earth's gravity assist in 2004, and it reached to the target asteroid Itokawa last September. It stayed at for 3 months around the target asteroid, and it completed the mapping, and also made the challenge of collecting samples of it. Originally, it was planned to be back to return to the Earth in June of 2007, but due to some incidents such as the fuel leak problems, they prevented it from it accomplishing it, and it's going back to the Earth in June of 2010, 3 years behind the original schedule. It's full of new technologies summarized here. This is the technology demonstrator. It's propelled by the ion engines, and it's also trying to have an autonomous navigation guidance using optical measurements. And it's trying to have a sample correction of the asteroid under a microgravity environment. And it tries to have a direct re-entry for the sample recovery from interplanetary trajectory. And it also combines the use of the low thrust with the Earth's gravity assist that was for the first time tried in the world. Spacecraft looks like this. Almost every instrument is concentrated to the back panel, the minus Z panel, what we call. It's descending to the asteroid on this surface down to the surface of the asteroid. And here is the cylinder-like device, which is a sample correction home to which the projectors are shot to the surface, and fragments created prime up through this funnel-like device to reach to the sample catcher inside the spacecraft. The spacecraft is propelled by the ion engines, whose apertures are open to the side panel here. Normally, the spacecraft and the altitude is pointed to the sun. The ion thrusters, the clustered ion thrusters engines are perpendicular to the sun direction. The spacecraft also carries a smaller robotic lander below, which was supposed to be placed on the surface to have the intimate and the close-up image observation of the surface. Trajectory is drawn here. The spacecraft and once placed on the almost circular orbit around the sun, which has an regular eccentricity with the Earth, and during which the spacecraft garners the trajectory energy with respect to the Earth, and it made the Earth swing by here, and the trajectory was extended, maximized, enlarged to the elliptical orbit to the asteroid Itokawa. The spacecraft is given the sophisticated image processor board. Every 2 seconds, the spacecraft photographs is on the surface with flash lamp on, and also another every 2 seconds, spacecraft photographs the surface with flash lamp off. The subtracting these 2 images will tell the spacecraft where the target marker is. Target marker is dropped and separately placed on the surface, and the target marker has a retro reflector on it, so that the spacecraft can identify that it's in the relative, in the horizontal the motion with respect to the surface. That's the basic strategy rather than making the spacecraft touch down to the surface. Spacecraft has operated the ion engines almost 26,000 hours by the 3 ion engines, and the spacecraft successfully performed the Earth gravity assessment of the Mail 204. Here's a comparison of the Hayabusa spacecraft with at least 10 enterprise missions. In terms of cruising, no spacecraft other than Hayabusa accomplishes the elliptical propulsion in landing with a target asteroid, and the Hayabusa is also aimed at a round trip flight for the first time. And in terms of the sampling, there's no spacecraft other than Hayabusa that has ever performed a stopover and bulk sampling so far. The spacecraft acquired the image of Itokawa at the end of July last year. The red circles indicate where the Itokawa target asteroid was photographed by the spacecraft, and the red arrows indicate how the trajectory information was updated, so that the photograph direction coincide right on the predicted direction. How these optical hybrid navigation was performed well is also glimpsed on this slide. At the end of August, the spacecraft also made the hybrid navigation and reached to the ecliptic plane while the Itokawa was seen on the direction of the constellation level. And when the ion engine was turned off, at a distance of 4,800 kilometers with respect to Itokawa, with a relative speed of just 9 meters per second. That's 32 kilometers per hour. That's a very slow speed and rendezvous. And the spacecraft gradually decelerates its relative speed to the target asteroid. And these photos are shown for at the beginning of last September. The spacecraft decelerates gradually and completely stopped with respect to Itokawa on September 12th last year. Spacecraft carries a filter wheel, this is shown, and on September 30th, after that they reach into the home position.
This is good news. Just want to let people know that the luncheon will not be till 12:15, so no one needs to rush out. And in fact, our luncheon speaker is sitting right over there. So go ahead. Sorry to interrupt.
Didn't want people to leave.
The spacecraft, photographs taken by the spacecraft is summarized in this movie. This is an Itokawa, the asteroid, taken from the 7 kilometers from the asteroid. Right. The spacecraft gradually lower is the position with respect to the target asteroid. The target asteroid is here, and until September 12th, the spacecraft was at 20 kilometers from it, and gradually it lowered the altitude to the several kilometers at the lowest a few kilometers from the asteroid, and changed its job key as a position, the horizontally to make a high phase angle observation. And let me note that to descend to the asteroid, no jet or the action of the system was fired. But the solar radiation effect that makes the spacecraft descend to the asteroid. After completion of the mapping, it started the descent and touchdown operation in November last year. The rehearsal number 1 was performed on November 4th, and navigation guidance practice was on November 9th, when the first target marker was released to verify that the image processing function of the spacecraft. And the second rehearsal was on November 12th, when the Minerva robotic lander was released. Unfortunately, it was not placed on the surface. And on November 20th, we had the first touching down for sampling operation. When the target marker number 2 was separated, that has the 880 people's names on it. And the 2 touching downs and 30 minutes long landing was accomplished on November 20th. And on November 26th, we had the second touchdown for sampling, during which we had 1 touchdown. And that instance, the sampling, the shooting command was actually issued. Here is shown that how the touchdown was made over the region above the 500 meters. Most of the navigation guidance was performed, based on the ground and the processing. And below which just 1 hour prior to touchdown, everything was left to the spacecraft to perform the automated touchdown. While the spacecraft released the target marker at the altitude of 30 meters, and the spacecraft itself and identify where the target marker is, and the approach to the surface, and to correct and cancel the relative velocity to the asteroid, and it touched down to the asteroid. Okay, so here is the target marker released on November 9th. As you can see, here is the target marker that has some kinds of stick on those are the very graceful figure, and the target marker was flown away from the spacecraft, as this slide shows. And the spacecraft released the Minerva robotic lander on November 12th. The spacecraft, the Minerva, returned to the Earth, relayed to the mother spacecraft, the photo roll its mother ship when it was just separated from the mother ship. So that the function of the robotic lander wasn't completely okay. However, due to the navigation guidance problems, we could not make it touch down to the surface of the asteroid. So we had the 2 touching down the candidates or area for sampling. One is the tip end of the Itokawa, that's called the Umer area, and the other one is the User C area. And this Umer area was found comprised of the many large rocks. This the red bar shows 10 meters, but the spacecraft extends the sample horn of just 1 meter, so that the surface was found not appropriate for the touching down. And this is for the laser proximity range finder that was used to measure the altitude, and also that there are 4 beams from that sensor to measure that the relative altitude with respect to the terrain was identified by this sensor. This is a closest image of taken on November 12th, and the radar I will show you much more the detail of the surface image, but this scale is 1 meter. On November 12th, we had the first descent and touching down attempt. The top figure shows the velocity information, just on the descent velocity information. The spacecraft studied here the vertical descent, and here is the instance of the braking to the braking speed to release the target marker. And This is the photo image movie of the when we had the first the sampling. As you can see that here is the shadow of the spacecraft, and the spacecraft approaches to the target point of the music seat. This point, the spacecraft approaches to this point very correctly, accurately. Okay, and the spacecraft, as this shows, very accurately guided to the intended point. Then we know that how accurate the spacecraft master and control its velocity. That with 1 centimeter per second relative velocity, makes the dispersion of 36 meters in 1 hour. Now think about the communication round trip time is 40 minutes long, from between the person and the spacecraft. So that the spacecraft had to control the relative velocity very accurately, probably a few millimeters per second. So that we accomplished this and the very accurate velocity control by through the terrain, based on the landmark tracking and navigation that was performed our project team. As this in the slides shows that we have the target mark correctly placed in the intended area here, and this shows that what happened to the first touching down event. The spacecraft, they reached to the 15 meters altitude when the spacecraft started hovering with respect to the surface, and just started immediately after the spacecraft detected an obstacle. The spacecraft has an obstacle sensor. Actually, there was not an obstacle, but any sequence after beyond that was cancelled, and the spacecraft was left, to wait for the ground command, and still while maintaining its altitude. Spacecraft made the first the touching down here, and the second touching down point here, and followed by the 30 minutes long standing on the surface. How we can tell that the altitude is shown here. That we had the altitude disturbances here. Those correspond to the touching down, touching downs. After that, the spacecraft, the altitude drifts about 10 degrees during the 20 minutes. That's exactly the exercise with the Itokawa rotation motion. And while the spacecraft persistently fired the action control jet system every second, but the spacecraft altitude was not restored. The spacecraft altitude looks like this, and the spacecraft was probably left at this altitude on the surface. On November 26th, we had the second touchdown. The trajectory to the surface is shown here, and also that we had the descent and the velocity information here. Here, the spacecraft started at the vertical descent, and here that the spacecraft descended its speed to the surface, and the spacecraft they performed the touching down here. Okay. And the spacecraft was very accurately guided by the real-time landmark tracking navigation, the tool developed by the team. And the spacecraft was correctly cancelled its relative velocity very accurately. This shows how the touching down was made on the second touching down. Here you can see also that the spacecraft shadow on the surface. The spacecraft then approaches to the almost similar point here is the target point here. The spacecraft then approached to the point here. You can see here the target marker, which was placed at the previous touching down. So that the spacecraft, the Itokawa, has now that the one target marker permanently, which carries the 880,000 people's name on it. The spacecraft started the hovering motion at the 7 meters from the surface, and they successfully touched down to the surface. But unfortunately, it was found that the spacecraft probably did not fire this projectile due to the software problem. But we have still the expectation of having a small amount of samples. Those may have been caught by the first touchdown event. The spacecraft and the altitude and the altitude motion on the second touchdown looks like this. Spacecraft started hovering 7 meters high, and basically on the use of the laser proximity sensors, the spacecraft altitude wasn't correctly aligned to this altitude. However, there must have been a kind of the slope change occurred in the spacecraft altitude. Actually, when it touched down, looks like this. Okay, and the spacecraft. This is not the corresponds to my scenario. Okay, but the spacecraft must have touched down like this. As I mentioned, on 26th, we found that the target was placed at the previous touchdown event on November 20th. The spacecraft carried four scientific instruments. One is an Amica visible imaging, and the nearest the near-infrared spectrometer, and also the laser altimeter and the X-ray spectrometer. And the spacecraft, the Itokawa, looks like this. The envelope box length is 550 meters, and the density was found a little bit lower than 2 grams per cubic centimeters. And the Amico completed almost 1,500 images. Those were taken, very successfully. And the near-infrared spectrometer, the LiDAR, and the X-ray spectrometer, those were also all functioned as planned. The global properties of the Itokawa is shown here. It's composed of two parts. Actually, it looks like a seal. This was not reported yet, but they have called this an object. This sea otter in Japanese language. Okay. So the spacecraft successfully made the observation of Itokawa. This is the front side. There will not be the distinction of front or the back side, but this is the front side that we call. This is the back side of the Itokawa. The extreme dichotomy is glimpsed from these two images. And actually, we called the every the terrain name the base name from our project team. The Itokawa has a very large boulders on it. This is one of it, whose size exceeds the theoretical limit. That's a very important point. And the enhanced synthesized multi-wavelength image is shown here. In which the fresh surface that is evident. It looks like in higher slope area. The details will not be shown here. We had the X-ray, the spectrometer information, the observation here, and also the near-infrared information here. I wanted the AV, the video people, not to record from the several images from now. Okay, those were not published yet. This is a very important point. I want the audio visual people not to record the several images from now, right? Okay, this is one photo whose resolution is 6 millimeters, and taken from the 59 meters from the surface. And what is evident is no debris was found over the larger rocks, and the debris entering into the gaps between rocks. That might have been caused by the shaking motion over the asteroid. And also that this photo whose resolution is 8 millimeters, and we can see that something here that looks like cement, but looks like I'm not so correctly familiar with this, but there might be a dredger. What the experts say, I do not know what it is. Okay, so this is an enhanced black and white picture of the surface, And what was seen here is white, not white portion corresponds to the steep area, and shaking motion that may have caused a slide, something like a slides, that to show that the pressure surface. And also this is the music C area, smooth terrain area, and we have some dimples on this smooth area, and also that accompanied with the rocks, on the surface. These dimples may have been caused by secondary rocks that may have hit to the debris area. And this is the composite and the synthesized image of the asteroid. This point is very near to the actually touching down point. This point was in here like this, and this length is 1 meter. So this length is about 10 meters. So how that they find that the surface is, and the magnified like this, and this is 1 meter, the length, and this says that the moons and the nebulous is much more fine, and this reveals how large the nebulous particles are on this small body. And we have that these three images, and we have that this portion can be reconstructed, in 3 dimensions. And here is shown that the information. Okay, how flat this surface is, you can see. So important thing is that surprisingly the this smooth area is flat. And some of the different mechanism must be present, making the surface so flat. That is also a very important point. Here comes another the photo. The boulders appear to be in the gravitational stable conditions, as you can see. And also that the clusters of boulders are found those in the circled area. And most boulders are not buried by the pebbles or the rebels. That is also an important point. But here is the boulder, the alignment is seen. And it tells us that this nebulous moves to this direction. And what was found is if density is common to nebulous and the rocks must subside. But there must be another simple mechanism that accounts for this terrain status. The dispersive pressure may have caused this surface. The dispersive pressure is also a new word to me. It's probably seen also in the mud and stone mixed flow on Earth, on the Earth. And this tells us how low the gravity is on this asteroid, and the correction of multiple rocks is a typical evidence of shaking. And even the slow slide motion may be a gash on this Itokawa asteroid. Right here is shown that the gravity, the vector information. The flag of the area is here, and this is the direction of the rigorous motion. Okay. And we had another problem in the new fuel rig on December 8th, and from that point, the spacecraft had lost the communication with the ground station. But that was restored on January 23rd. From it, the spacecraft started its attitude control using the xenon gas for the ion engines. And currently, the spacecraft restored its attitude successfully, and the spacecraft is operated normally every day this month. And the spacecraft returns to the Earth 3 years behind the original schedule in June of 2010. And currently, we have completed the ion engines verifications. And it turned out the 2 engines were already verified, and that they were operable. We found that they were operable, and we think that spacecraft can be returned to the Earth in 2010. That's all.
Thank you very much. We appreciate it. I apologize due to the time. We're not going to take questions. One more note, if you are a member of the Planetary Society, your names are on that target marker along with almost 1 million other names. Your names came back with stardust, and your names slammed into and vaporized with the deep impact missions. So you're all out there. Thank you very much again.